Right now in the DevHeads community, we're implementing finite state machines in FPGA fabric. We're here with Navdeep, one of DevHead's resident computing experts. Hey, Navdeep, why do developers struggle so much, especially early and mid-career ones, with the complexity of FPGAs?
Hi, Brandon. Often developers tend to zone out from the complexity it adds in terms of primarily software and then board design, routing, etc., not being aware of how exactly FPGAs can adapt to bring value addition in their system. Certainly, FPGAs are not for all the applications, and few things to look at considering FPGA, whether the FPGAs are suitable, are the performance requirements, and if there is a need for flexibility, and also any custom hardware or accelerators are being implemented in the system. I prepared a demo that explains how easy is it to implement a finite state machine design in using hardware description language, which is a building block for any FPGA system to be implemented moving forward. So this solution is on AMD Zynq 7020 FPGA, which can be adapted to any other system as well.
Great, let's take a look.
We have the system implementation setup shown over here. So it starts with the system clock. Look at the left side, where it is an inherent clock in the FPGA of 125 megahertz. It is further fed into a clock divider Verilog module, which brings it down to 3 hertz, just for the case of visually showing them over the LEDs on board. Then this 3 hertz clock goes into the LED pattern module, which is a Verilog block in FPGA. And this pattern module has inputs such as mode and reset in the case of synchronous. Mode is the user button, which is the 2-bit input having 00, 01, 10, and 11 states to select different patterns of LED trails. And then we also have a reset signal for the whole system, output being 4-bit for the LED on board again. And that's the outer block, and in the inner block shows the dotted one, which is asynchronous finite state machine setup. The only signal which adds on to it is the tick, and the whole clock input is cut out in case of asynchronous one. This is a project definition where we have the LED pattern sync.v file. This is a Verilog module for the as you seen in the block diagram earlier, and then we also have a wrapper, which is a clock divider module, similarly as in the block diagram. Adding on to this is the constraint file, which is board specific. So this constraints file comes to use in the implementation phase of the project, which defines what are the pins for the hardware peripherals which are interfaced. So onboard components are chosen and they are assigned certain pins. For example, in our case, these are the 4-bit LEDs, push buttons, and certain state selecting switches. So looking into the LED patterns in Verilog code, we over here have the LED. Okay, we here have the Verilog module defined with LED pattern sync name, and it has the mode input, clock input, and the divided clock output, along with the output for the 4 LEDs. The 4 states are defined over here. Then we have a whole state machine with the state transition cases put over here. Then these 4 are the actual LED switching logic, with state 0 being no LEDs on, state 1 being there's a flow pattern happening to the left and 2 right, and then there is also a single LED on, which is the 4th state. We'll see this right on the demo, and let's switch to it. So now I'll go right away and program the device. So LED pattern bit stream is chosen over here, programming it. Device. So the default state being currently the initial starting state is S0, which is all the LED off, and which is kind of evident from looking at these switches. So now I'm selecting a 0-1 logic, which is the state 1. We should be seeing the LED trail moving from left to right, and then the 1-0 with the LED trail moving to the opposite side, and the final state 1-1, which is just a single LED on. This is about the demo for the block diagram and the code which we saw just now, and how easy is it to implement a hardware description language solution using state machines in FPGA.
So this is synchronous mode. What about asynchronous mode?
Yeah, okay. So coming to asynchronous mode, it's evident from the block diagram that we have seen the whole clock is cut. So if I go back to the code, and we can see over here in the asynchronous. So looking at this asynchronous mode implementation, if you look at the module, we do not have any clock source at all. So one additional input added is the tick button. And this is the only change by getting rid of the clock. So this tick is a user input and will be controlled by the finger taps by the user. Rest implementation remains similar unless there is no clock divider module as well for this. So we'll switch back to the Vivado and program the asynchronous bit stream for the same project. Now this being done, if we look at the device state now, it's again is evident that all the LEDs are off. And if we go to 0, 1, that's the first state, there are no LED trails. This is for a reason that we have cut the clock and the system just waits for a positive edge of the trigger, which is user input tick. So once that I give that, you can see the LED trail starts moving. And if we go to another state, then we'll see the LED trail moving in opposite direction with the same tick switch, and the same as well for the final state where there's a single LED on. This is about asynchronous mode implementation.
Well, that's great. So we've implemented a simple function in FPGA Fabric, but that's not the only thing that developers might be challenged with when they're working with FPGAs. What are some other areas where they might find roadblocks?
Yeah, right. So other thing can be with the sensor interface. So we look at how to get the SPI and I2C peripheral up and running in FPGA using Vivado block design, and also by implementing custom IPs. So other thing can be that now system on chips are coming up with tightly integrated programmable logic and processing system together. We'll see how to have the OS running in the ARM core and as well implement custom user IPs in them. So that's another challenge which user might face, and we'll certainly tap into it.
That's great. So Navdeep, in the meantime, where can developers go if they're looking for help around FPGAs, tips, tricks, best practices, etc.?
So for help or to learn more about developing solutions with FPGAs along with these examples, like we have seen now, you can always visit DevHeads GitHub repo, where the contents of the demo will be put open source. And also I'm at the Discord server, NGU25, where I'm always available to answer your questions based upon embedded systems and FPGA topics.
Great. He's at NGU25. I'm at TechieLou. You can find us and all of DevHeads resident and engineering experts in the Discord server, which is linked to on screen and in the description below. We'll see you in the server.